All right, Mark. Shashank. Every week, there's so much news. I said it last week. I said it the week before. Like, I'm always just, like, mind blown with, like, how fast this space evolves. Crazy. So just last week was Nvidia's GTC conference. Shashank, did you go to that?
I watched a live stream of that after the fact, a recording, and I had to like stop a couple times and try to take it all in because there were tons of numbers, very, very technical, lots of transistors, lots of bandwidth of computing, lots of bandwidth of additional networking on top of that computing, a lot of memory, and a lot of different jargon words that were thrown at us.
Yeah, my background is like software, and a lot of this hardware stuff is somewhat Greek to me. So I feel like I'm just like somewhat riding the wave a little bit, where it's just like they say some words, I get confused, and then he says some words I understand, and then like I'm like, all right, I'm following you, I'm getting you, and then he's like going off on like Planet 9. I'm like, okay, I'm confused again, but I guess that's just life technology.
Let's try to dumb it down a little bit and get to the meat of the announcement. So they introduced a new chip called the Blackwell, which replaces the Hopper in the H in H100.
Oh, is that what that stands for?
I believe so, yeah.
Oh, Hopper. So
yeah.
Hopper 100.
Yes.
Do you know what the A100 stands for?
I forget. I'm not sure.
Okay. So anyways, we're talking about the GPUs, so the graphics processing units from Nvidia. For those that don't know what a GPU is, I assume most people listening to this podcast like already knows what a GPU is, but a GPU is just a kind of like a component within a computer that was specifically made, I think originally designed for processing like graphics or like, rendering like images. So like if you have like your computer and like your computer is going to like display something on a screen, you're going to need some sort of GPU. Now, some computers will have a discrete GPU, so like a separate component, and then other computers will have an integrated GPU, like all on one board. So if you get like a MacBook Air, they're not going to have a separate chip for a GPU. It's all going to be like on one like integrated chip. But it's still going to have like some sort of GPU in it. So Nvidia, they are the number one makers of GPU probably in the world right now. Or I should call them a maker, but or maybe I call them more like a designer.
Mm-hmm.
But anyways, because as we mentioned in a previous episode, TSMC is the one who actually makes the chips, but Nvidia designs the chips. And the chips that Nvidia is like most famous for is the GPU, and you're going to use the GPUs for playing a bunch of games. So as we mentioned, like the H100, the A100, the RTX, all these things, it's just different versions of the Nvidia GPUs. And you were saying that the new one called, what was it, Blackwell?
That's right. So it's B instead of an H. So instead of the H100, H200s, we have the B100 and GB200. So taking a step back, continuing your train of thought, they started with graphics for video games mostly. And then they noticed a bunch of researchers in various parts of the world in various domains like genetics, protein folding, things like that, trying to use these GPUs for processing parallel data and parallel computing, which requires lots of different computations running at the same time, but doing less work than a CPU would, which in contrast takes like one big task and does something very complicated in sequence. So these new researchers, sparked an idea in Jensen's mind, the CEO of Nvidia, Jensen Huang. And he started slowly investing in CUDA, the software framework that optimizes code to run on these GPU transistors in parallel. and optimizes the amount of work done by these GPUs. So as they started building this software to optimize parallel processing on hardware, they coined this term accelerated computing. So it's not just this general purpose CPU that's being used for everything. You make, specialized chips that are focused to a specific task. And in crypto, we had all these ASICs that were specialized computing to just compute the hash for to create a new block.
Okay, so I think there's a lot of things, like a lot of terms being thrown out here.
There's a lot of things.
So let me try to dumb it down as much as I can for me, really.
Sure.
So all right. So first we mentioned a GPU. The GPU is a particular component of a computer, a chip, you may say, that is specifically made for graphics. Its primary use case would be like video games, but like maybe like people who are like making movies and stuff can use that. Another chip which we mentioned is the CPU. So the CPU is just kind of like, I don't know, like another way you think of it is like a Swiss Army knife. It could just kind of do like any type of processing. Where like the graphics card, like the GPU is, the graphics processing unit is like mostly going to be for like video games or like graphics, machine learning. The CPU can kind of handle anything. And then Shashank, as you mentioned, like we have those two. Those are typically you're going to find in like your standard run-of-the-mill computer. But there is also like people who or like companies that will make specific chips for hyper-specific like applications. So like a GPU is more specific than like a CPU, but it can still do a lot of stuff. But then you mentioned ASICs, which is, I forget what it stands for, ASICs. It's like
application-specific integrated circuit?
Yeah, application-specific integration circuit. So it's like one that is made for specific applications. The one that I think is like super famous would be for like Bitcoin mining or Ethereum mining, where people are making specific computer chips only for Bitcoin mining. Well, you could run a CPU or you could use a GPU for that. It's just not going to be nearly as good as a chip that is like completely made for that particular task. So anyways, go back to what you were saying.
Yeah, so the TLDR is they released a bunch of new stuff, and the new stuff is 30 times better than what they had about a year ago.
Impressive.
That is like a ridiculously big number.
Wait, 30 times?
30 times.
Over the last year?
Over a year ago. Yeah. So, that's a ridiculously big number. You don't see that in computing.
30 times. That's insane. That is literally insane.
Yes.
So like, because Moore's Law.
Correct.
Like, so Moore's Law, like, I think, like, was it Gordon Moore?
Yeah.
Is his name?
One of the founders of Intel.
One of the founders of Intel, he noticed that, like, the number of transistors on a CPU, I think, would double every 2 years.
Roughly 2 years, 18 months.
In other words, like, the speed of compute would double, like, every 2 years. So you're telling me it's not double, but 30 times.
Yeah.
That's insane.
So settle down. We have to kind of dig into these numbers and the nitty-gritty of the presentation to understand what is actually going on. So I was talking about the Hopper chip and the new Blackwell chip that's supposed to replace this old chip. The new chip is a bit bigger. It has 200-something billion transistors. The old chip had like maybe 70 billion or something. It's kind of like they made the old chip a little bit bigger and then glued two of them right next to each other with a very high bandwidth connection.
Oh, so it's not like it's actually 30 times better.
So that's part of it.
There's two of them.
That makes it maybe, what is it, like 2x better or so, 2.5x better.
Well, but like, would it really be 2x better if it's just like, if I take chip 1, chip 2, smash them together, and now it's like, you have double just because like you double the size.
A little less than double, but they actually made the original chip a little bit bigger, and they stuck two of them.
Okay.
So it's a little bit bigger than the original chip. The B chip is a little bit bigger, and they stick two of those chips, and then they put two of those joint double chips into a board with another CPU, and they call that the GB200 GPU.
Okay.
So they need the CPU to kind of coordinate, schedule, manage all these tasks that are being run by these GPUs to optimize the LLM, both training and inference. And they go into really in-depth in this presentation. They try to focus on improving training speeds and also inference speeds. And these two different workloads require slightly different amounts of precision.
So, by the way, training is when you're creating new large language models. So you're trying to create ChatGPT from scratch. You're trying to create Gemini, whatever. You're trying to create one of these new ones. Inference is you're trying to use the one that's already trained. So both interesting, but somewhat different tasks.
Yeah. So it's kind of like this new revolution happened. It really took off 2 years ago. Not that they weren't aware of transformers and deep neural networks. He took us through the history of Nvidia, and they were thinking about this since 2012 when image recognition algorithms first came out. And those were deep neural networks too. But yeah, continuing the story of the new chips. So they take these chips and they, have this amazing animation where they, glue two chips and then put these two glued chips onto a board, call that a GPU, stick a CPU to help coordinate these two GPU chips, stick that in a rack with maybe like 8 or 10 other GPUs, and then take that rack and put 8 of them. And then next to 8 of these, you have some other networking racks. And then you have this little cube of racks that do tons and tons of processing.
How big are these racks? Like bigger than a car?
One rack is like a vertical column. It's about as tall as a person. And
like about the size of maybe a refrigerator?
No. Maybe half a refrigerator.
Okay.
It's a little narrow.
Okay.
And then you have maybe like 8 of these. I don't know why. It goes in powers of 2 maybe.
Okay.
And you have an additional 8 racks that don't have GPUs. They just have a bunch of networking equipment. So the 30x improvement that they were touting really comes into picture when you think about all of these networking switches, the wires, the cables that take all this data back and forth between the GPUs, and try to optimize the amount of speed, the cache hits, misses, keeping everything in memory right next to the place where it needs to be computed. And then, you do a bunch of matrix multiplication, some fancy math in one GPU and another GPU that's far away in a different rack. You have to combine and reduce the operation of of these two GPUs. And to do that, they really focused on all of this networking. They call it NVLink. And that is really what's pushing this new field beyond Moore's Law. And they actually came up with this at the end of last year. So at the end of last year, they touted similar performance gains. They said it was 15x faster than the previous generation. And this one is 30x faster than that original generation. But since the last release, it's about 2x.
Okay. So what you're saying is that the GPU is only marginally better.
Correct.
Than last year. I mean a little bit better.
Yeah.
But there's all these other
in line with
things
Moore's Law.
kind of next to the GPU or surrounding the GPU, which is improving. And there's
Exactly.
you kind of combine all of these little tiny micro optimizations together, and then you get 30x.
Yeah, because if you rewind maybe 5 years ago, I don't think anyone on Earth, any company on Earth was doing computation like we're doing today with a 1.8 trillion parameter model from ChatGPT that is running in production today. That is an insane amount.
So that's really big.
That's ridiculous.
It's really big. Yeah.
So the forefront of computer science was focused on ARM chips, the little tiny chips that Apple designs and sticks in your iPhone that doesn't need to coordinate with other chips and doesn't need to do a whole lot of work. It needs to be fast, power efficient, and fit in a little coin-sized compartment on your phone.
Yeah.
But this thing is massive, and they're all working together, which is kind of different from traditional cloud computing, where you could have tons of servers, but they're all doing kind of different work for different clients, or not really combining large amounts of data and computing together.
So it seems to me like there's almost like two independent tracks for chips. Like track one is where you're getting like more powerful chips that are smaller and more power efficient.
Yep.
So I guess that would be like what you find in like your iPhone, or like, I don't know, like your smart glasses, or like, different
Smart
like
rings,
smart device, smart watches, stuff like that. Like, I mean, like I would imagine like an Apple Watch would have been like impossible like in the past, because like you couldn't have such like a powerful chip that was so tiny, right?
Absolutely.
Like, I mean, there's a lot of stuff that is just improving, and this seems to be like the polar opposite of that, where it's just like bigger chips working together, using a bunch of power, and like almost like you're not even trying to make the chips as small as possible. You're just trying to get like as beefy, as most power as you possibly can. And maybe there is trying to like be some optimization where like, I guess, as opposed to having like, the amount of power that would take to like power a house or something like that. Maybe like you want half a house. But I think that like in general, I feel like a lot of the people who are buying this stuff from Nvidia, like, the exact amount of power probably doesn't really matter. I don't know.
I wouldn't say that.
No?
I wouldn't say that.
Okay.
No. Because I think I had a rough understanding of this back when I first joined Google like 5-6 years ago, and we had this internal talk about how we build data centers. There's a bunch of criterias. You need cheap electricity. You need cheap water. You need political stability. Cheap land.
What do you need the water for?
Cooling.
Oh.
Yeah. So these machines generate a lot of heat, and that's another one of these innovations that Nvidia is working on. They design liquid cooling for this entire rectangular cubicle of racks. It handles cooling and performance to run these things at high performance for everything, including the GPUs, the networking switches, and everything around it.
Okay, so you're saying like, in order to have a data center, like all of these things are important. Like
very important.
The energy is important. So like you want cheap energy, I assume, close to water. So like
So speaking of cheap energy, I did some rough math. They showed a rendering of a hypothetical data center with their entire new line of chips, and it had some, I don't know, like 600 exaflops of computing. It's like a mind-blowing number.
600 exaflops
is like a massive number. So for context, we kind of work with like giga, the number giga, which is a billion.
It's like, like a gigabyte. So like for context, like how big is like a movie? Maybe like I was gonna store like a movie like on a computer. Would that be like maybe a gigabyte?
Depends on the encoding, but yeah, a couple gigabytes.
So maybe like 2 gigabytes, something like that.
Sure.
Okay.
Something like that. So we're kind of moving from memory, storing something, to how fast you can compute things, which is kind of thought of in flops, floating point operations per second. And I think your phones, the latest computers, can do computation on the order of like a couple teraflops, which is a trillion floating point operations per second, a step above giga. Then, you combine all of these things into data centers, and you think you have a really cool rig with these thousands of chips, and then you get to a petaflop. But Nvidia took it an order of magnitude above that. not just like 1 or 2 exaflops, 600. It's like 0.7 zettaflops. It's like just massive numbers.
Okay, so I'm trying to like wrap my mind around these numbers.
So it is roughly 600,000 times faster than your personal computing device.
I feel like that doesn't help me. So like, what's the brain? Like, how many flops would the brain be? Is that like, I feel like I've heard that before. Is that like 20 petaflops or something like that?
It says 10 to the 17.
So, because an exaflop is...
That is close.
That is the 18.
That is a little less than an exaflop, yeah.
So, okay, so if the human brain is 10 to the 17.
Sure.
So that would mean an exaflop would be an order of magnitude more. So that'd be like times 100? Like 100 times more? No, is that 1,000? Is that 100 times?
10 times more.
Oh, 10 times more.
Yeah.
Okay.
17 to 18.
Okay. So if the human brain is like 10 to the 17th.
Yep.
Which is 1 petaflop. Is that right?
No. It is 100 petaflops.
Oh, 100 petaflops.
So this would be 1,000 times more. This Nvidia hypothetical data centers with 680 something exaflops.
Okay. So I'm starting to get it. So
it was like 1,000 times more processing.
So 10 to the 17th is 100 petaflops.
Yep.
Now, 1 exaflop, 10 to the 18th.
Yep.
So that would be like a group of 10 people like working together, like in 1 exaflop.
Sure.
Like if I'm thinking like brains, like 1 person.
If we're making a 1-to-1 comparison, but the architectures of these neural networks and the human brain and, the agentic, form that they take is very different.
Well, sure. I'm with you, but at the same time, I'm just trying to like, wrap my head around this into like knowledge of compute that I understand. So this would be like a group of 10 people all working together. And now that's 1 exaflop. This is 600
massive
exaflops. So what you're telling me is that like, as opposed to like if 1 is 10 people, 600, that'd be, what is it? 6,000 people? Am I doing the math right?
Sure. Yeah.
Yeah. So 6,000 people.
Yeah.
That's like bigger than a lot of companies.
That's a lot of intelligence. Yeah.
That's wild. I mean, if you get like another 30x improvement, like, I mean, you're going to be reaching like...
simmer down there. So I think they were able to get these large improvements because this is a new paradigm of computing. This is not something that they'd seen before. It's not something that they optimized for before. So I think they're tackling all the low-hanging fruit, trying to optimize like the networking stuff, trying to focus on scale as opposed to before where GPUs were, a single GPU or maybe 2 GPUs in a machine on a personal computer. So I don't know what other low-hanging fruit we might have unless we switch to like a radically different architecture. Or one fun new startup that I saw, which was building a chip where the design was hard coding a transformer architecture onto the chip.
Okay, so that's almost like an ASIC.
Yeah,
in that case.
Yeah, for a specific transformer snapshot with a specific set of weights.
So, for reference,
I think
the transformer architecture is the the computer, the architecture, I guess, that is used to create all of these large language models. So this was there was a paper published, I think it was in 2017. Where some researchers at, I think it was like Google's DeepMind, they came up with this. They designed this. They designed this architecture for the computer, and then based off of that, we were able to create all of the large language AI stuff that we have today. So if you could have a specialized chip that does that, so remember, like a GPU is generally made for graphics, but people are using it for machine learning. Hypothetically, if you made a chip that was specifically made for LLMs, you could make it way more powerful than what exists today. So to me, that seems like a massive way for improvement. So if Nvidia right now can get the equivalent of like 6,000 human brains, who knows? Like in the future, we're going to be able to get like maybe 60,000 human brains like relatively soon. I mean, that's like the size of some small, that's like the size of large universities.
Yeah.
Like the entire computing power of like, or brain power of the university, just like there. If we get like another 10x, I mean, that might be like, what, 600,000 people. That's like small cities.
Yeah.
One more 10x, that's like 6 million.
And it keeps getting cheaper.
Yeah, we're at like countries, right? And then like before you know it, in a few years, or like maybe next year or something like that, if we get another 30x improvement, who knows? We'll be at like the computing power of the entire human race.
Yeah. How many doublings do we need before we get there?
I feel like there's a little math problem because what's the human race right now? That's like 7 billion, 8 billion, yeah. 8 billion people. So, assuming that, let's say like one human, or like, what do we say? 10 humans is one exaflop. So I guess it would be 6 billion divided by 10, and then that'd be the number of exaflops that we need. But then I guess you'd have to do the number of doublings for that. I don't know. I saw you typing. Did you have a calculator?
I just tried to Google like how many powers of 2 would you need to get to 8 billion, and I think it's like 30. So roughly 30 doublings, and then we get
30. That doesn't seem right.
Yeah, well, we get a billion after 30.
Okay, so if we get like a doubling, let's say every 2 years, 30 billion. That'd be the entire human race that we would have there.
We get 8.5 billion after 33 doublings.
Assuming that's okay, 33 doublings. So that would take like 70 years at this current rate.
Yeah.
So I guess in the year 2024. So wait, 70 years roughly. So 2024. 2094.
That's if Moore's law keeps continuing, but as we've seen, Nvidia has just blown past Moore's law 1000xing performance in the last 10 years.
Okay, so that's assuming doubling once every 2 years.
Sure.
But if we can get 1000x, we're gonna reach like the entire human mind share by like, I don't know, next Thursday or something.
So we had a couple other topics that we wanted to talk about too. What do you think we can do with this doubling and really fast computation, specifically as it relates to robotics?
Okay, so changing the topic a little bit, but gosh, the more we talk about this, just the more excited I get. Like, oh my god, like the implications are wild, just wild. We're gonna really issue in an age of abundance, I think. But so Nvidia, again, it's been a common theme on this topic. They just announced their new Project GR00T. So I think that, like, in general, lots of compute is super exciting. But like, it's only half the battle, right? It's if you think about it, like, we have like unlimited energy from the sun, but like we only capture some tiny fraction of that. The rest of the earth that hits, or the sun that hits the earth, is just like radiated off into heat, and we're not like directly capturing that to use it. So it's like, it's one thing to have the energy, it's another thing to like capture it and use it. So the same thing can be said for robotics. Just because we have like the design for humanoid robot, that doesn't necessarily mean that we have the software to be able to run those robots. So Nvidia announced something at their conference last week, or earlier this week, that was super cool. The Project GR00T is software that is used to train humanoid robots. So my understanding is that the robots are able to take inputs from various like images or videos or sensors, whatever. And based off that input, the robot is going to be able to take an action, and then iterate based off of that action. So in other words, what that means is a robot could potentially watch somebody cook a meal, and then maybe after watching that person cook a meal a few times, maybe it'd be able to cook you a meal. Maybe the robot could watch you landscape your lawn. By the end of that, maybe it would be able to do the landscaping, clean your house, vacuum, wash windows. I think that while we're not there yet, I think this is like a really exciting first step to getting some sort of like home robot companion, and like, robots just like everywhere helping us do things. Yeah.
No, I mean, it was really exciting. The demo that they showed is analogous to how we have these large foundation models, and then you take that and maybe like fine tune it with actual training data, or give it a couple examples in the prompt, like the system prompt, and use that as a reference to learn new behavior. So these robots are being trained in Nvidia's Omniverse, which they've been focusing on for a while, and it's finally like kind of paying off for robotics.
The Omniverse different from the metaverse?
It is a simulated accurate to the laws of physics virtual environment, not for human beings, but to render environments, simulate what would happen in a factory, simulate maybe like hazardous conditions in construction, or more recently, train robots to navigate, take action, and do things in a virtual environment, and have them learn repeatedly on like fast forward, and then take that learning and then stick it in a real world robot.
Okay, so the Omniverse is just a simulated world for robots.
For training, speculation, understanding how different events and scenarios would play out in a different environment.
Okay.
So one example that they gave was the Amazon warehouse, where they had a bunch of simulated boxes with realistic physics engines, a bunch of human puppets walking around, moving boxes, making a mess, dropping stuff over. And they had robots that were stuck on pre-planned routes. And instead of getting stuck when there's a bunch of boxes, they had an orchestrator with a bunch of cameras that can see everything everywhere in the warehouse. And it tells a robot, hey, there's something blocking aisle 4. Take this different path to get to your destination. And so with the analogy of like an LLM, they're training all of this movement, actuators, pathfinding, and giving you a general robotics model. And then you can take that and then fine tune it. Like you said, show it a few examples of folding clothes, making like coffee latte art, and then you can do it.
Wow, man. I think that's so exciting. I think, with these large language models, it's really cool to do knowledge work, like, write a book, tell jokes, do things that have like to do with input into a computer. But I think it's like a whole nother level of interesting to have a robot interact with like the real world. Because I feel like in general, it's not there. I think we had this conversation before, but like the LLMs are getting to a point where like I think that at a lot, maybe most tasks, they are like probably equally to as good as what a human, like the average person, and even like maybe better than the average person would be able to do, right? Like I think that like
we're talking about LLMs, not
LLMs. Yeah. Like LLMs right now like are super good at like writing jokes, translating documents, writing text, writing code, all these things, right? And I think that like we're getting really close to where they're almost like as good as humans. But like the robots right now aren't really anywhere near as good as humans, right? Like I mean, I've never seen like a robot tie somebody's shoes. Maybe it exists, but I've never seen it. I've also never seen like, I've seen like, maybe some robots make like latte art, but those robots are like super specialized at making like drinks. And also like it takes way longer than a human. Like, I don't know if you ever tried to go to like some of the robot latte art things. It's like, it's not that fast.
Yeah.
You have to wait a while. I mean, like, it's perfect every time, but like a human can do it like faster. So like to have a general purpose robot that can, just be taught anything, that's really exciting.
That's so freaking exciting. Yeah, I think robotics is a very different field. It's been focused on large, repetitive tasks at scale. And that's really the only scenario where it makes sense to deploy robots.
So like that would be something like
a factory line,
like building a car.
Even making like little toys if you make enough of them, iPhones. And you usually use those with scale when you're doing doing one thing a lot of times, when you need precision, when you need them to be really accurate, and when the payoff is substantial, because like these things are very expensive, with like their upfront costs being very expensive. But I guess with a general purpose robot that can go into any scenario and do any task, that like opens up the world and all the opportunity. That'll be really exciting.
Man, I am so excited.
I do think it'll take a couple years to play out.
Maybe more than a couple. I don't know. What do you think? What's your prediction? I feel like we have to wrap up soon.
Yeah. So I think we also spoke about Figure AI, which had their humanoid robot, and I think I might have misspoken. I might have said that they were showing something sped up, but going back and rewatching some of those videos and demos from other robotics company, these things are running in real time.
Wow.
They're able to respond to user requests, take action, all in real time. It is very impressive. So I would say maybe, like a year or two for these demos to reach some real world use, and then maybe another few years for the next generation of products. So I wouldn't be surprised if we have robots that people can buy and use in their daily lives in 5 years.
Okay, I can see that. So what you're saying is maybe it'll take another 2 years for like the researchers to figure it out. These like general use cases.
I think it'll take like a year or two for the existing demos to reach actual users, and maybe another few years for the researchers now to build something that the average person can use.
Okay. I could see that. So 5 years, like I'm buying my robot butler, and then maybe in 10 years,
robot gardener maybe.
Okay, sure.
Yeah.
And then maybe in 10 years, I'll be able to get it and it'll be like actually affordable.
Yeah.
Yeah. Because like I would imagine that in 5 years it'll be super expensive.
It'll become like an iPhone at some point in like 10 years, where we're just churning out models every year or two.
I hope so. Well, anyways, on that note, we gotta wrap up. But thanks everybody for an awesome week. We'll see you in the next one.
Until next time.